Thank you very much for accepting my invitation. This is a part of like efficient machine learning seminar series at Gerald, and your title perfectly matches the objective of the talk. Thank you very much again, and yeah, floor is yours. Please go ahead.
Okay, thank you very much, Wade. Today I want to talk about a current project that we're having at Andrea Lodi's lab about the a library called Ecole, and also maybe the kind of background behind it, the kind of research that has motivated the development of the library, and the kind of work that's been being done in this sub area. So to get started, this is joint work. So I should acknowledge also the collaborators. So this is joint work also with Justin and Lara. And Justin is a master's student at the chair, although he's moving to do his PhD at Toronto. And Lara is a PhD student at Delft in the Netherlands. Antoine is the main developer and is actually graduating very soon. He's a PhD student of Andrea. This is also work with Maxime, who is a researcher at the lab right now, and of course, Andrea, who is the big boss. All right, so the general context of this area is what we could call repeated combinatorial optimization. So that's quite common in industry. You end up repeatedly solving similar combinatorial optimization problems. So, there's many examples I could give. I guess the prototypical examples would be an energy distributor such as Hydro-Quebec would repeatedly solve combinatorial optimization problems to meet power demand at minimum market cost. So they have to decide on how to allocate power across different lines. And the shape of these combinatorial optimization problems tend to be always the same. They're always unit commitment problems, or more specifically, they tend to be security constraint unit commitment problems. And every day, say, or every 15 minutes, the data inside the problems, the specific numbers that go inside the problems are slightly different. But the overall shape of the problem is the same. So just a bit of general background. How do you actually solve these kind of problems? What does Hydro-Quebec do here? Well, the common approach would be as follows. You might first formulate them as integer programs. So integer programs kind of serve as universal languages for these types of combinatorial optimization problems. They're simple. They're problems where you're minimizing a linear objective in some variables with some linear equalities and inequalities. But with the specific, so they look like linear programs, except that there's a specific additional constraint that those variables are integer. And the fact that those variables are integers makes the whole difference. Right? It makes those problems pass from being solvable easily in polynomial time to being extremely hard. And some of them are basically so hard that they cannot really be solved by computers with modern technology. So they make a really, really big difference to add those additional constraints. Now, the fact that, I'll put a caveat here, the fact that combinatorial optimization problems can usually be expressed in integer programs doesn't mean that you necessarily always want to do that. Sometimes it's better to have, say, an algorithm that's been specially designed for a class of problems. So for example, maybe you have a SAT problem, binary satisfaction problems. You could express them as integer linear programs, but you probably don't want to. They're specialized solvers just for those. So this is more kind of the Swiss Army knife approach. This is something that's going to work in general. You might have specialized approaches for specific types of problems that work better, but this is but for many problems in real life, this is the one main approach that's actually being used. Let's say that it works like 90% of the time, or this is what people might do 90% of the Okay, and now after you found a formulation of your problem as an integer linear program, then you just throw it to a general purpose MILP solver, and you wait and you collect the solution. So there's a lot of solvers that are out there that can be used. Some are commercial closed source solvers for which you need to pay for a license, such as Gurobi and Cplex. There's also some that are open source, such as Skip. Okay. And how do you choose your solver? Well, ultimately the metric, the thing you're trying to get here is to solve your problems as fast as possible. This is how solvers distinguish themselves. And in fact, the competition is very cutthroat, and they will, put out ads in specialized magazines about how, hey, the new version is like so much faster than the competitors, were so much better. So speed is really the name of the game here. They cannot really compete on quality of the solutions in principle, since, in theory, they all end up with the same solution at the end. So really, then the main thing to fight for is the speed at which they get that optimal solution. And yet, even though these solvers have been around for a while, this has been an approach that has been around for a while, in some sense, these solvers are still dumb. These algorithms are still dumb because they treat every problem as if it was a new problem. And yet in real life, like I said, the companies, they often solve similar problems over and over again. You have tons of examples out there. Beyond Hydro-Quebec needing to meet power demand at minimum market cost, you have also stuff like, logistics. How do you route packages with airplanes in factories, in warehouses, for example, or airplane companies having to schedule crews, or cloud services companies having to distribute tasks across servers, or you have taxi companies that need to assign drivers to passengers. Those are all examples of combinatorial optimization problems, and they're solved repeatedly. But those solvers don't take into account that. It's like every time they see a problem, it's like the first time they've ever seen such a problem, which leaves a lot of potential on the table. So here's an idea that's something maybe smarter that you could do. Maybe try to exploit statistical similarities between the successive problems so that you get faster and faster at solving these problems. And how do you do that? Maybe with machine learning. So that's the core idea. Okay, and that has motivated a lot of research. Actually, there's been, especially since the mid-2010s, a flurry of new papers that have come out on trying to accelerate the solving of problems by exploiting statistical similarities. Now, I guess I need to put a little bit of a caveat here. I will say that in some ways you can maybe look back at stuff that people were doing before and retrospectively reinterpret it as being a form of machine learning or a form of specialization of solvers for problems. For example, solvers have been for a while sometimes tuned to achieve they might have hyperparameters, and they've been tuned on some data sets of instances to achieve best performance. So you might see it as a very primitive form of machine learning here. But it's not necessarily very, very deep or systematic. It might treat the solver as just a black box, and you're not necessarily trying to play with the internals of how these solvers work, how the algorithm actually works. And also, you might see some algorithms that are used right now in those solvers as internal components as being primitive forms of machine learning as well. So I might get into that a bit later, but there's stuff like in branching reliability pseudocost, or just pseudocost. It's just a branching strategy that can be regarded as a very simple averaging scheme in taking decisions. And that can be regarded as a bit of machine learning. But again, there's no, very strong systematicity in how these methods have been applied, and it's not like there's been machine learning people that kind of stop and look at those things. What's new is there's starting to be more direct interest in machine learning people with a proper statistical formulation of the problem that have started looking at these problems, and the results are really interesting. So more precisely, how does this work? So how did they achieve this? Well, all those solvers, those MELP solvers, they're basically based on the same basic algorithms, something called branch and bound. So branch and bound is basically kind of divide and conquer algorithm. What it does is it recursively builds a tree. So I guess I need to give a bit more details about it, but what it will do is it will look at the problem and then divide it into two subproblems, where it's going to decide, okay, I'm going to look at the subproblem that's identical to my first one, but with an additional constraint, either that a variable is smaller or equal to some integer, or greater or equal to that same integer. And this forms a partition of the feasible space. So in particular, clearly, wherever the optimal solution is, it must be in one of those two subproblems. And then what it can do is it can solve the LP relaxations, the linear relaxation of those subproblems, which are the same as the problems themselves, but without the integer constraints. And that can be done very efficiently. There's efficient polynomial time algorithms for solving linear programs. And if the solution that you get happens to be integer, great, good. That gives you a feasible solution. If it's unfeasible, you are at a dead end, you stop with that branch of the tree. And if it's neither of those, then you might further subdivide the problem and try again. So you progressively, by subdividing those problems, develop a tree, sometimes ending up in at an endpoint, either because you find an integer LP solution or a dead end. You find infeasibility of the linear relaxation. And yeah, repeatedly you need to take decisions. Namely, you need to select which one of the leaves in the tree am I gonna next subdivide. And also there's a choice in the subdivision of which variable do you pick to divide the problem over, and around which integer. And the choice of integer is usually, there's a standard scheme for doing it. Namely, you're gonna look at the linear relaxation solution and pick a variable that's fractional and go around this midpoint. So that's kind of okay, but the choice of variable that you're gonna branch on and which leaf in the tree you're gonna develop next, that's really not obvious. And it makes a big difference on the speed at which you're going to solve the problem. So that's quite important. Yeah, that's roughly basically how this branch and bound algorithm works. You repeatedly alternate between this leaf selection and this variable selection.
So, Didier, may I ask you maybe a dumb question? This part, then branch and bound looks like a binary tree that we already observe in like classification trees in machine learning as well, where building these trees is easier in the sense that we have a specific criterion how we can go down and split the variable. Yes. So do you think that like these two problems can get connected in the sense that perhaps there is a certain criterion that we can use that it's easier and more intuitive to do the branch and bound, borrowing something from the more efficient algorithms coming from machine learning?
Well, at least with the decision trees, right? There's like a standard cart algorithm for how to subdivide the tree. Yes. That's greedy, and probably not. It's definitely not optimal. I mean, I don't think that it globally maximizes the global loss, right? So already in the first place, those decision trees, they're not the standard algorithm already is kind of imperfect. This is imperfect as well. So I mean, I see the there's obviously a high level connection between the two, but I'm not sure that there's enough interconnections between the two that it's useful to transfer one to the other, mostly because, say, for example, say somebody had come up with something very clever with decision trees and found that some kind of algorithm that would help them solve the problem globally. Then maybe it would be helpful to transfer it to this branch and bound. On the other way, I don't know. Okay, put differently, I think something interesting about the branch and bound algorithm, maybe a difference between the two is the branch and bound algorithm, no matter how you take those decisions, you kind of always end up with the same solution at the end, you know, the optimal solution. So what makes a difference is only the size of the tree that you get at the end. Ideally, you want it to be as small as possible. But in the decision trees, I guess in principle, you care less about the size of the tree that you obtain. Your ultimate objective is just to get like as high an accuracy as possible, for example. I don't really see that many connections, but I know of some work of people at MIT that I think it's basically the group of Bertsimas that are doing those optimal decision trees, and they have this kind of I think they're basically using an analogy with a bit kind of like branch and bound to try to globally optimize decision trees, like basically trying to find partitions that are like that get optimal training accuracy. But it's very expensive, I think. So that's the closest connection that I can think of. Yeah, that's all right. Okay, so back to this. So in addition to node selection and variable selection, there's in practice, there's also a bunch of bells and whistles that make this much more efficient. So there's primary heuristics. They're basically subroutines that can be called at any point during the solving. And from time to time, the solver might decide to run them. They're not guaranteed to succeed. So their objective is to find feasible solutions, but they might fail. So it's kind of a gamble, you know, you're kind of wondering, okay, should I spend the computational time and roll the dice and maybe I will get the feasible solution or not? You don't want to run too many of them because that might be too expensive. But at the same time, you know, if you roll the dice and it comes out right and you do find a feasible solution, that's great for the process. So there's a delicate choice here of which of those and when those primary heuristics you might want to run them. Some have a higher chance of success but are more expensive. Other are more light but have a lower chance of success. So, and there's not a lot of mathematics behind it or kind of like formalization of this problem that helps you guide your intuition here. So cutting planes. So that's something else also. It's basically additional constraints that you can add into the problem that tighten those LP relaxations that you get. And the question is, so you have generic algorithms to produce them. The question is maybe you don't want to add them all inside your problem because they might tighten your problem, but at the same time, those LPs are harder to solve because there's more inequalities in them. So you need to balance between having some of them inside the problem, but not too many, so that the LPs are not too hard to solve. So this is tricky as well. Preprocessing, I mean, you know, you're given a formulation at the start for your problem. So an expression of your combinatorial optimization problem as an integer program, but perhaps that's not the best one. Perhaps there's another formulation that has less variables, less constraints. Maybe the LP is just better for solving. And so the solvers, they will have kind of predefined routines that they can run to try to reconfigure the problem. And the big question is which of those preprocessing routines and in which order do you want to run them? So that's not obvious at all. So in practice, what you really have in those algorithms, in those exact combinatorial optimization algorithms, is a sequence of decisions. It's a sequential decision-making problem. You have variable selection, node selection, cutting plane selection, choosing which primal heuristics to run, choosing which preprocessing routines to run, many other things as well that I haven't talked about, like simplex initialization, things like hyperparameters. Yeah. And it's really not clear how you take those decisions, and they all interact with each other in very complicated ways. And there's basically very little theory behind how you choose these things. So those solvers right now, they have rules that have been designed by humans in them, right? They are, so basically operations research experts sat down and thought, this sounds like a good way of picking the variables. This sounds like a good way of picking the nodes, etc. But they are, and those rules are really good. It's really not easy to beat them. There's been many decades of attempts at designing excellent rules that are gated by human intuition. But that's exactly their problem also. They're limited by human intuition. And you might think, can you do something better? Can you have better decision-making policies that you could choose here? And this is exactly where machine learning can help. So from a machine learning point of view, if you look at this, these are really Markov decision processes. So a Markov decision process is a mathematical framework that looks at these kind of sequential decision-making problems as they are being an environment that is in a given state and might transition to other states. And an agent evolving in this environment that might take actions. And traditionally, after taking an action, this agent might receive a reward for taking this action. And its objective is to maximize its reward in the long term. The rewards are usually chosen to be something that ultimately is the ultimate objective here. So it might be, for example, solving the problems as fast as possible. So that's traditionally very successful. It has led to many very impressive advances in machine learning.
Just a small point, Didier. This t time that defines the state is continuous or considered to be integer?
No, it's integer. So it's integer here as well. So those are not continuous MDPs. Those are discrete MDPs. Actually, maybe I can give more details. I was going to talk about it a bit later about how it's going to look like in this context. But here, you should really see the solver as doing the following thing. Say you look, for example, at variable selection. Well, the solver will first start, do a bunch of things, and then at some point, path is going to end up having to choose for the first time a variable to branch on. And then it might ask the agent, the policy, hey, which among all this pool of variables, which one should I select? And the agent can base itself on the whole state of the branch and bound process so far to take its decision. So the problem itself, all the information it can gather about the problem, stuff like maybe the LP relaxation of the problem so far, maybe other statistics about the process. And then it will take it will pick a variable in a certain way. That's the agent's job. And then the solver will be, oh, thank you. So it's going to branch on it, blah, 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 do a bunch of things. It's a black box. And eventually it's going to hit again another decision point for selecting a variable at another node. And it's going to ask the agent again, hey, okay, now in this new state, in this new node, which one of those variables should I branch on? So it's really sequential integer value time. Puff, and eventually the process ends. And when the process ends, it's because you've solved the problem, you've found the optimal solution, you're done. You've found the optimal solution and you've proven that it's the optimal solution. That's when the branch and bound process ends. But I'll talk about it a bit later. In any case, these Markov decision process formulations they're excellent, and there's a bunch of machine learning methods that have been developed for finding good policies, finding good ways of taking actions in different states that have been very successful. They've led to, for example, policies that play the game of Go very well, or stuff like multiplayer games, even now, like StarCraft 2 or Dota 2. They have been used also to manipulate robots, so those are continuous actions, but rather successfully. And they have had industrial applications as well. So, for example, famously, Google uses reinforcement learning to control the cooling in its data centers. So quite successful. And these methods have started being used also in this machine learning meets combinatorial optimization area, and very successfully as well. So we're starting now to have workshops, we're starting to have tutorials, we have surveys, and it's starting to even have an impact back into the traditional combinatorial optimization community as well. For example, there's this famous combinatorial optimization book by Wolsey, Integer Programming. In its second edition that just came out, there's now a small section about machine learning methods in combinatorial optimization. So that's quite cool. Okay. So let me give maybe like a few concrete examples of what these kinds of works have looked like. Not a lot, but still. So one of the earliest very machine learning papers that came out is Ecole from 2014 that was published at NeurIPS, a very early work in this area. And what they're looking at is the node selection. So which leaf should you branch on next? This actually, they decided to do imitation learning. So there was an expert and did this, and they tried to imitate the expert. And for whatever reason, you cannot really use the expert in real life, in practice. So you're trying to find a good approximation of it that you can actually use to solve problems. So in their case, their expert was something called a kind of diving oracle. And the reason why they cannot use this expert is because this expert is cheating. It's a policy that requires knowledge of the optimal solution to try to solve the problem, to take its decisions. So basically, to use this oracle, you first need to solve the problem once, find what the optimal solution is, and then you're trying to solve it a second time using knowledge of that solution. But the second time you're solving it with this technique, you do very, very well, because knowledge of the optimal solution is an excellent way of there's an obvious way kind of how to behave in the branch and bound process and node selection.
It somehow gives you an idea about what must be the optimal graph.
Yes, I mean, what you can do is basically shoot straight for the optimal solution. And then after that, you have the question of how do you end up the process, like end up proving that this is, the actual optimal solution. But just doing that leads to excellent trees. But of course, you cannot use it in real life because, of
course, you don't
you don't want to solve the problem twice. Once you've solved it once, you're done. But it's maybe an excellent way of getting gold standard examples of state action pairs that you can try to imitate. Can you do basically, if you try training a model to imitate that behavior, maybe it's going to pick up on stuff, even if it doesn't actually have knowledge of the optimal solution. Maybe it's going to pick up on stuff and realize patterns in how to take actions in given states that will maybe imitate a bit the diving oracle.
Yeah, maybe also you're solving a similar problem that has been solved before, so you know the optimal solution for a previous one.
So that's true also. I mean, in practice, you will learn on a collection of similar examples. So maybe, for example, all the solutions tend to have something in common, for example, that the model might be able to discover, but the human might have trouble seeing. So the algorithm they use is Dagger. That's a pretty standard imitation learning, active imitation learning algorithm. The model was pretty simple. It was just an SVM. This is kind of pre-deep learning, or like simultaneous at that time, where deep learning was starting to get pretty popular, but they didn't jump on the wagon immediately. So it's just an SVM. And the metric that they use, what they prove is really, they prove that there's improvements in optimality gap over skip and go beyond for problem classes when you put a time limit. So if you can't solve the problems to optimality in a reasonable time, the next best thing that you can do is put a time limit and say, let me get at least the best solution that I can find within a given time limit. And they show that they get better solutions within an arbitrarily set time limit than the default solvers. So that was quite good, but there hasn't really been any follow-up work on that specific one. Another one is a paper that I contributed to. So that was done by the lab, by Andreas lab. And it's, we did imitation learning for variable selection instead. So the expert here was not an oracular expert, but it was something else called strong branching. And strong branching is a way of doing variable selection that is empirically shown to be really excellent. It takes excellent decisions, but it is extremely computationally expensive, to the point where it takes so long to take its decisions that in the end, when you look at the overall time needed to solve the problem, it's not competitive. But if you take all the time you want to look at examples of good decision making, that would be like an excellent one to try to imitate. So the goal here is basically to learn an approximation, a cheap approximation of this expert, one that can take decisions hopefully close to being as good, but much faster, and fast enough that it's actually competitive. The algorithm was just pure behavioral cloning, so that's just basically classification, the simplest thing you can do. And interestingly, the model was a graph neural network. And this is because we came up with a representation of the branch and bound states that was a bipartite graph. And that was nice because MIL problems have inherent symmetry in them. Namely, you can permute variables or constraints, and this is still the same problem. And with these graph representation that we had, there was a natural encoding of that symmetry as well, because you can permute the nodes in the graph, and this is still the same graph. So that was quite nice, and we showed improvement in the size of the branch and bound trees, and also the time required to solve problems on over skip, so the open source solver. Best open source solver on 4 problem classes. So that was published in 2019. Another nice work that was recently published last year at ICML is one on cut selection. So this is reinforcement learning. So they actually did reinforcement learning for selecting a single cut. So, it's not quite there in being useful in practice, but it's still a big improvement. And they used evolution strategies to do that. The model was an LSTM. That's how they dealt with the fact that problem sizes could vary. And they showed improvements in dual gap over human baselines on 4 problem classes. Finally, another one that was done at the lab is something a bit more black box, but more on the preprocessing side. It would be, say you have a mixed integer quadratic program. So those are, unlike ILPs, those are problems that have also quadratic, as a quadratic objective, but it's still integer valued. And a classic problem with those is you can choose to linearize them. So because they're integer, you can transform them into an equivalent integer linear program. And the question is, do you want to? Because there's also algorithms that can deal directly with the quadratic objective. And it's not exactly clear how you choose those two. It's pretty much a black box. So what they did is they just took a bunch of MIQPs, look at how long it takes them to solve them if they're linearized or not, and they train a random forest to try to decide that, and they show that compared to the default strategy to linearize in CPLEX, it gives improvements on a class of customly generated MIQPs. So that gives also a good example. So anyways, there's a lot of such examples that I could give you. But there's a big problem behind all of this, is that in practice, these are usually pretty big engineering efforts. So this is one of the reasons why so far there's an obstacle in actually using this in industry. And even in academia, those are not easy problems to tackle. You might need a combination of, this is really interdisciplinary work, you need a combination of both operations research and machine learning expertise to succeed well in those kind of projects. And this is where the library we're developing comes in. So I finally get to the main point of this talk. So right now we've started developing a new library to help with these kind of projects. Okay, so I might give a summary here so far of what we've done. So what is combinatorial optimization? We've seen it's basically optimal allocation problems. Where does machine learning can help? Well, when you're repeatedly solving them, which often happens in industry. How can it help? Well, because when you're solving these problems, you're doing sequential decision making inside the solver in the algorithms. And why has it not been widely adopted yet in industry, at least? It's there's just a high barrier of entry for these kind of problems. Now, if you look at other areas where there's MDPs, where there's imitation or reinforcement learning, there's been a lot of work done in developing good software to simplify the projects in these areas. In particular, in 2016, there's been this library, Python library, that has been developed called OpenAI Gym, that has clearly very much accelerated research in imitation and reinforcement learning. So, for example, it offered like a collection of standardized environments and intuitive API. It was easy to install. It was open source. It was very nice. And there's a lot of people that have started developing their own libraries after different topics, different places where there's MDPs that kind of mimic this library. It gives a very intuitive way of formulating problems. So it basically formulates MDPs. And the code kind of looks like this. So it's pretty simple. You first define, you just pick one of the environments that are predefined inside a problem. Then you might loop episodes over the MDP. You start your episode, and then repeatedly you'll simply pick an action based on the observation, on the state, and you will tell the environment, okay, do a step and get me to the next decision point, or tell me if the episode is done. So the new library that we're designing is basically something very similar, something that's basically kind of an OpenAI gym for combinatorial optimization. It offers a very clean gym-like interface to skip. So we decided to build it on top of the best open source solver. And it abstracts away how solvers work so that in principle, at least, people can focus on the machine learning. Perhaps the best way to look at it here is that skip is really the environment in this setup, and Ecole offers you a nice interface to over the state, the rewards, the actions, and the agent. So this is still under development, but it's already usable. So we have both right now a configuration, so that's hyperparameter selection environment that's offered. Also the variable selection one is done. We have, actually, it's a bit out of date. We have one coming up very soon for also primal heuristics that's going to be available. So you pick a task, you pick what you want to improve. Do you want to improve the variable selection? Do you want to improve the cut selection, for example, something else? And in addition, you choose what kind of observation, what kind of state you want. So we offer predefined, pre-coded states that give you information about the problem. So for example, the graph bipartite representation that we used in the Learning to Branch paper is already coded in Ecole. We have also a flat representation that comes from a paper of Khalil from 2016. We now have another one for configuration as well. We're implementing one from a paper of Hodder from the group of Kevin Nathan Brown for like algorithm configuration that's going to be there. So it's going to have quite a bit. You pick your reward. What do you want to try to optimize? Do you want time? Do you want number of nodes? Maybe primal dual integral, something like that. And it's nice. It's very fast. We coded it in C++, but there's a nice thin Python API on top of it, so it's very intuitive to use. It's very easy to install. We really made sure that anybody can get started very quick. So it's available on Conda. It's now available on pip as well. So for the machine learning practitioners, they usually know those tools. This is very easy to use. We try to think very hard about the defaults so that out of the box, you might already have sensible defaults. If you want to deviate from those defaults, you can, but at least, you don't have to think about a million things. It's extensible. If you think that, oh, the library is missing something, it's easy to add to it. And it's open source and it's free, of course. So as a code example, the code looks like this. So you might, and it looks a lot like Jim, you might say, for example, oh, I want a branching environment. So that's the variable selection. Then you say, okay, I'm going to do 1,000 episodes on it. So I'm going to solve 1,000 times problems. You tell it, okay, start and solving the problem on this instance. You might give it a path. And then you're going to get the state that you might have pre-decided in advance in the constructor, an action set, some reward. And yeah, otherwise, you just pick according to whatever way you want, which variable you want to branch on, for example, and you pass it to the environment and it's going to move into the next state. It's quite extensible. You can change a lot of things. So the reward function, for example, we have some basic arithmetic on it. So maybe you want to optimize instead, say, the square of the nodes. For example, you could easily do that. You can select which observation function you want. Those solvers, they come with a lot of hyperparameters. You can change them as well. And also for people that just want to kind of play with it and don't necessarily have like a nice data set of problems to solve, it also comes shipped with a collection of instance generators with sensible defaults. They're the same actually that we use in the branching paper. So that's nice as well for like just playing around and trying different things. Algorithms. And it's nice also for people, say, machine learning that are doing, say, RL research and are looking for very hard problems, but might not really know, might not have a specific combinatorial optimization use case. They're just looking for hard environments to tackle. And the main value I can see from this library is, well, it reduces the amount of people that that need to be working on such a project, hopefully. It's also less debugging. Presumably a good chunk of what used to be code inside the project is now debugged because it's part of Ecole and it's been extensively used and therefore extensively debugged. It allows for much faster experimentation. It's standardized as well. It means that maybe if people, different papers start using the library, they'll have the same basis to compare things. So it's not always the case before. So anyways, for more details, you can go check. We have a paper out at a workshop at the last NeurIPS from last December that you can see. We're also sending out right now a longer paper that we're here waiting to hear back from. And I'll also say this is quite new, but for the next NeurIPS, we are actually organizing a competition that will be using the library with a bunch of people in the area. And we really highly encourage you to come to participate if you're interested. We think it's going to be quite cool. So it's going to go from July 1st to October 31st. And there's going to be 3 tracks, 3 tasks, if you want, in it. So there's going to be a primal task. So the goal will be to produce feasible solutions in order to minimize the primal integral over time. So that's basically finding as good as possible good feasible solutions in a limited amount of time. Then there's going to be a dual task as well. So that's going to be variable selection. Actually, the metric is going to be the dual integral, the kind of dual of that. There's going to be also a configuration task that's just going to be pure black box optimization of the hyperparameters of the solver with the primal dual integral as criteria. So, so there's a website. I encourage you to go check it. But we hope to see. We already have quite a bit of interest from different participants, but it would be nice to have additional people. And that's basically it. So we have a website, ecole.ai. You can go check it, and the documentation also is moderately extensive at this point. So you can go check that out. That's it.